Hello, my name is Jay, and today I'll be talking about inductance. So first is mutual inductance. And so this concept of mutual inductance is basically around this setup of two rings. If you have ring 1 and ring 2, each with their own current. Ring 1, with a current that can be dependent on time, produces a magnetic field that goes like so, like the arrows point in the picture, that produces a magnetic flux through ring 2. However, from Biot-Savart, we know that the magnetic field is directly proportional to the current running through ring 1. And so using this proportionality equation, we also know, because of how magnetic flux is related to magnetic field, we also know that the magnetic flux is directly proportional to the current running through ring 1. This relationship between the magnetic flux through ring 2 from the current running through ring 1 is defined as this mutual inductance constant. And in this case, it is what inductance means. It is the proportionality relationship between the flux and the current. However, with self-inductance, now we only have one ring. It is the relationship between the flux through this ring and the current running through that same ring. And so self-inductance, or as you normally just say, inductance, it is a property of the geometry of usually a circuit, but it could also be a conductor, the geometry of a circuit that relates the magnetic flux to the current. And so inductance is really just this constant that we've given it such that it relates these two things. So it is not a function of time, but rather it is a function of how this circuit or conductor is set up. So if it's in a different shape, then the inductance will change. If if it tries to maximize flux or minimize flux, then the L of the circuit will change. But if the geometry and the setup of the circuit doesn't change, then it's a constant. And so what can inductance, or self-inductance, be used for? The most important use of inductance is adapted from Lenz's law. So we know from Lenz's law that a circuit will try to oppose change in magnetic flux, for a closed circuit. And it's written as the EMF induced is equal to the negative change in magnetic flux. But we know from the last slide that magnetic flux for any closed circuit is equal to Li, right? It's related to the current. And so what this means is inductance also measures a circuit's ability to oppose change in electric current. And so that's what that means from, if you go from this equation from left to right, right? So to the left side, you have Lenz's law, but then you plug in Li for the flux, and you say inductance is what measures how strongly a circuit opposes that. The last little math tidbit is for magnetic flux through a three-dimensional object, if it has more closed circuits, if you will. And it's the concept of flux linkage. And so it's the concept that the more closed circuits, right? So if normally we model inductors as these coils, right? So these solenoids. the more coils they have, theoretically, the more flux that goes through it. And so flux linkage is this kind of intuitive, or it's supposed to be intuitive, reasoning that the total flux through this inductance, this inductor, will be more the more loops that it has, right? Because there's more flux going through it. And so this is really the last tidbit that you need to know for inductance. And the rest is really just an application of all of the equations on the formula sheet to try to, either find inductance or use inductance to find some other thing. And that's really it. That's what inductance is, and hopefully it helps you to use it. This should be it for this video, and see you in the next one.